For 70 years, physics told us solar panels had a hard limit. Recently, AI broke it and mapped 380,000 new ways to generate power. Here is how the grid changes forever. But to understand how this AI pulled off a miracle, we have to look at the exact moment the rules of physics changed. A few weeks ago, scientists fired one photon into a solar cell. More energy came out than went in. To understand why that matters, you need to know three problems that held solar back for decades, and how AI just broke through all three. Sunlight looks like one thing, but it's actually made of billions of tiny packets of energy called photons. They're raining down on us right now, every second, everywhere. A solar panel is just a surface that catches those photons. When a photon hits the right kind of material, usually silicon, it knocks a tiny particle loose. That particle starts moving. That movement creates a flow. And that flow is electricity. That's it. No burning, no spinning turbines, no exhaust, just light bumping into atoms and making them move. And here's the wild part. The sun sends enough energy to the Earth's surface every single hour to power all of human civilization for an entire year. Every hour. So, why aren't we using it? The answer is in these three walls. Nobody had answers to any of them. Wall 1 isn't bad engineering. It's the universe having opinions. There's a ceiling, about 33%. That's the most sunlight a regular silicon solar panel can ever turn into electricity. Not because we haven't tried hard enough, because physics says so. For 70 years, that ceiling didn't move. Here's why. Sunlight isn't one thing. It's a mix of colors, each carrying different energy, and silicon can only fully use one narrow slice of that mix. The rest? Some colors slip straight through, too weak to do anything. Other colors hit too hard, and the extra energy burns off as heat. Either way, most of the sun's gift just goes to waste. Then somebody found a strange crystal called perovskite. You can paint it on like ink. And here's the trick. Stack perovskite on top of silicon, and they share the work. The top layer grabs the high-energy colors silicon can't fully use. The bottom layer keeps doing its job. Together, they break the ceiling. Almost 35%. Higher than physics said was possible for silicon alone. But perovskite has a problem. It's delicate. Rain wrecks it. Heat wrecks it. Even sunlight wrecks it. To make it tough, you have to find the one perfect way to arrange its atoms, out of millions of possibilities. By hand, that would take longer than the sun has left to burn. So we didn't do it by hand. DeepMind's AI did it in a week. It found 380,000 new stable materials. Humans, in all of recorded history, had found 20,000. And these aren't ideas on paper. Companies are shipping these panels right now. The ceiling isn't gone. But for the first time in 70 years, we can actually reach it. Wall 2 is simpler to explain and harder to solve. The sun turns off at night. Clouds happen. Seasons happen. The planet spins. And a grid that goes to zero every evening is a grid that needs a backup, which for a century meant fossil fuels got to stick around as just-in-case infrastructure. Batteries chip away at this, but the deeper problem is chaos. A power grid serving millions of people is being constantly balanced, supply versus demand, millisecond to millisecond, against weather patterns, human behavior, industrial load. It's too much information, changing too fast for any human operator. DeepMind's grid management models can now see a cloud forming 20 minutes before it arrives. They reroute power from sunlit regions, pre-charge storage, and smooth out the drop before it ever hits. The grid doesn't feel the shadow. Cities in South Africa and India are already running above 95% renewable energy, consistently, around the clock. The sun still sets, but the darkness stopped being a deal breaker. Wall 3 used to be money. It basically isn't anymore. Solar has dropped 99% in cost since the 1970s. In the sunniest parts of the world right now, it's producing electricity at 2 cents per kilowatt hour. Cheaper than coal, cheaper than gas, cheaper than most bottled water per unit of energy. The last remaining wall is infrastructure. A 20th century grid built like a one-way pipe, designed to move power from a few giant plants to millions of passive homes. It wasn't built for millions of small generators feeding energy back in. AI is now being deployed to turn those dumb copper networks into something more like a nervous system, predicting flows, rerouting in real time, balancing micro-generation from rooftops alongside utility-scale farms. The hardware problem is essentially solved. What we're upgrading now is the grid's ability to think. So, that photon, the one that produced more energy than it brought. The effect is called singlet fission. One photon hits the right material, and instead of freeing one electron, it frees two, a 130% quantum yield. For 50 years, one photon, one electron, was treated as the ceiling. A fundamental rule. Turns out, it was just the floor. And this was discovered not by accident, not by a lucky grad student, but by an AI systematically working through material configurations that no human would have prioritized. We didn't find it. We built something that could find it for us. Here's the part I find genuinely strange and kind of beautiful. The AI systems that cracked these solar problems are themselves enormous consumers of electricity. Training a large model, running data centers 24/7, it's a serious energy appetite. So Google, Meta, and Microsoft are now building solar farms directly next to their data centers. The intelligence that figured out how to better harvest the sun is now being powered by the sun. It's feeding itself, and the loop keeps tightening. None of this means the energy transition is done. Grids take years to rebuild. Mines are still operating. Not every roof has panels, but the direction has locked in. Every remaining obstacle, material stability, grid management, storage, cost, is now being attacked by systems that don't get tired, don't get bored, and iterate faster than any research team in history. We've crossed a threshold. The question used to be if solar could compete. That question is settled. The question now is just how fast. And the answer to that is changing every week. For 150 years, we powered civilization by burning things that were once alive. Ancient sunlight, stored in carbon, dug up and released. We were living off an inheritance. Old light, dead light. What's happening now is different. We're finally learning to catch it fresh, directly from the source, in real time, with nothing wasted. Not the echo, the thing itself. If you like this video, watch our fusion episode next. It's about the moment AI learned to control a star on Earth. This is Vital Horizon.